Now we're going to introduce the topic of linked lists. An array is a data structure. A data structure is a way of organizing information in memory that makes it easy to do certain types of things. And so there's a large number of types of data structures. And in fact, there's enough that there's an entire course devoted to studying data structures. Linked lists will be the first of the data structures that we will construct ourselves. But first, let's start off by talking about a potential issue. So if I had some code, and of course we would assume we have more than just this, but if in this code I create this variable p, which is a pointer to int, and I don't give it an initial value, then what does it point at? Well, remember that since this is a local variable, it comes into existence when this block is executed. And all we're writing here is the instructions to give us a block of memory to store the address of an int. But this doesn't say anything about giving an initial value. But that block of memory contains a bit pattern, and that bit pattern could be interpreted as an address. So the answer to the question of what does it point at is, well, I don't know. The issue is, how do I distinguish between the bit pattern here that is garbage and therefore doesn't really point to a block of memory that I need to access, and containing a valid address to a block of memory that I can do something with. So the way to distinguish between the two is that we can assign it an initial value of null, written in all uppercase letters like this. So here's a program where we create these two variables. Num is an int with an initial value of 3. Num pointer points to an int, and then maybe eventually in here I would give it the address to num. And once it contains the address of num, then I can work with that address and dereference it to get to the 3. But what if I forget to do that? Well, if I assign an initial value of null here, and then eventually work down here and ask the question, does this contain the address of num, or did I never get around to assigning an initial value? Well, then I can check. If these two are different, that means that it does point to something. It could technically be something that I freed up, so it still could be a problem. But we're going to make the assumption, at least in this case, that it points to valid memory. And so then I can dereference that address and get to the 3. But if I never assigned an address to num pointer, then it still contains the value of null. So I come down here and say, oops, and it has this value. And of course, in reality, I would do something about that. There's lots of combinations of how to deal with this, but this is a simple case. So let's talk about what a linked list is. It's a collection of nodes, each of which contains some data that we're interested in storing, and then they're linked together. So this node here contains 5 in this case because it's simple, but it could contain lots of information. But right now it contains the number 5, but it also needs to point to the next node, because these are not necessarily in contiguous memory locations like in an array. So wherever these are at, the only way I can find them is to look in one of the other nodes. So this node contains the address of this block of memory. So when I come over to here, I can work with the 6, but to get to the next node in my list, I would follow the address here to here and keep working my way down. This symbol here is like a ground symbol in an electrical circuit, and what this means is that the last address in the linked list here will be null. That's my way of working my way down the chain and eventually stopping because I no longer have an address to a valid node. So how do we create that? Well, before we put the pieces together, let's see what a node looks like. It's just a struct. So this node struct will contain the variables for the information we wish to store, but it also eventually stores the address for another struct node. It would be illegal to say struct node X, for example, because you can't store a structure within itself. But I can store the address of a structure within that type of structure. So in the previous picture here, each of these is a structure. And typically with a linked list, they're dynamically allocated structures. and then we store the address of each new node in the previous node. So this is what we call singly linked lists. There are other types, and we're not really going to get much into that, but I mentioned those briefly at the end, or at least one particular one. But why would we use a linked list instead of an array? Because if we go back to this picture, it looks like I have 5, 6, 9, and 2 right next to each other, which is also what would be the case for an array. So why do we care about linked lists as opposed to arrays? Well, some of the pros of arrays are that they are contiguous memory locations, which means that we can find other elements in the array by using column offsets. So if you say, given the address of the current element, what number is 10 ints away from here, I can use pointer notation to find the new address. All right, we can't do that with a linked list. And arrays, since they're typically a built-in data structure, are easy on the programmer to use. I like using arrays. Linked lists take a lot more effort. What are the downsides? Well, what if I need to insert something? So for example, if I have this is an array. I have 1, 2, let's say I have 7 and 9, and we'll assume there's some other memory here that I haven't done anything with. Right, so I'll just put X's. What if I get the number 5 and I want to keep this list sorted, which means 5 needs to come between the 2 and the 7. Well, as it is now, the only way to do that is I move the 9 over to here, move the 7 over to here, so now this contains 7, this contains 9, and then I can put the 5 here. In this particular example, that's not really that much work, but what if there were a million numbers or a billion numbers? Well, then there's a lot of computational effort to doing that. And also keep in mind that I could have an array of structures. So instead of just moving a couple of numbers over, I might need to move entire structures containing lots of information over to new locations. And also, I can't really remove things. If I say, well, I want to remove the 5, well, I can't really just remove it. I mean, I guess in some sense I could mark this location as no longer being used, but it's still a block of memory. But then I also could do the reverse of what I did before, where I could say, well, then now I'm just going to copy the 7 over to here, copy the 9 over to here, put something back in here indicating that's a quote-unquote unused spot. But that still requires computational effort. So that's one of the downsides of working with an array. Also, in general, I can't free up the memory allocated for an array. If it's statically allocated, so if I use the static keyword, well, then that array exists forever. If it's a local variable, so it has automatic storage duration, it exists as long as the block exists. I can never, while that block exists, just say, well, I'm done with this array, so let's free up the memory so the computer can use it for some other purpose. So then lots of the pros that we have for the array are the cons for a linked list and vice versa. So looking at the pros here for a linked list, I don't need to know how much memory in advance to allocate. Whereas for my array, if I say, well, I think I'll need to store 10 numbers, but maybe it's only 3 numbers, well, I still have to allocate memory for 10. Now, we did see in my dynamic memory allocation videos that we can use realloc to actually sort of get past that idea. But that, of course, still requires a lot of work to move things around. So here we don't typically know in advance how many nodes we'll have in our linked list. It's easy to insert new things. How's that? Well, if this is my linked list, and we typically call the pointer pointing at the beginning, the head. So let's say it goes here. So we have 1, 2, doing what we did right here, 7, 9. And you say, well, I want to insert 5. How do I do it? Well, one way would be to add another node down here and move everything over. But we're trying to find an advantage of this over an array. So what I can do is create this node, give it the value of 5 we had, because remember, each of these is stored in different places in memory, and I don't actually know their physical relationships. I just know that to find 2, I look at the address in 1. To find 7, I look at the address in node 2, and so forth. So then what I can do is tie this to this, not in this order because I would have just lost track of this. And by tying this to this, I break this connection. So now the order is 1, 2, 5, 7, 9. I never physically moved this node, this node, this node, or this node. Or change the contents of the nodes. I didn't have to do any of that. And also, we can then delete things easily. If I say, well, I don't need 5 anymore, I can always delete this in some order. I'd have to keep track of certain things because that's one of the potentials for bugs. But I can delete this block of memory, which really means freeing that block of memory, and tie the 2 to the 7. And once again, I didn't have to change any of these things other than change this address. So that's an advantage. And as I just said, I can free that memory because each node is dynamically allocated on its own, so I can free each one independently. So what are the downsides of working with linked lists? Well, they're not as easy to understand conceptually and to manage as an array. And just like any other form of dynamic memory allocation, there's a great potential for screwing things up, as we'll see. Or as you'll see as you write code, because you'll have lots of bugs. All right? So let's do some stuff first before we see an example of a better way to do it. So let's create a node definition. Struct node. Don't forget the semicolon right here. So I'll have a variable x that stores an int. Struct node star next. Now the first way I'm going to do this will be very explicit. Don't really do this way. But I'm trying to help you understand the big picture. So let's say we want to store the numbers 1, 2, 3 in some order. So I'm going to get 1, I store it. I get 2, I store it. I get 3, and I store it. So I might do this. So we need some variables. So struct node star head star temp star p. Why do I put the star on each of these? That is, why not just say this? Well, the way C works is it thinks what I just said is that this is a variable of type struct node, not a pointer to a struct node. So I need to include the star there. All right? So let's do this. Head equals malloc, size of a struct node. I want to let the computer figure out the size. I may look at this and think that here's 4 bytes, here's 8 bytes for an address, so it's 12 bytes, and hard code the 12. But there's certain situations where the computer may choose to pad the structure to put things in specific locations. And therefore, I may not really know the true size. So let the computer figure out the size for you. So this is allocated memory for a structure, but I haven't given any initial values. So now it exists, I'm going to say head, and this is a pointer. So I'm going to dereference that pointer and also work with something within the structure. So I'm going to use the arrow. So head x equals 1. And I want to terminate this linked list with the address of null. Right? So let's see what I just did. I'm going to actually need this, so I'm thinking about it ahead. Let's draw a picture seeing how I'm actually constructing this. So I want to store the numbers 1, 2, and 3. 1, so you get 1, then you get 2, then you get 3. So I'm doing this. I'm going to allocate memory. Head points at this. I put the 1 here, and I terminate this. So it means the next address is null. And then the reason why I created the temp variable is because now if I say head malloc, it will point to a new block of memory, but it no longer points to this. So I just lost track of it. So what I'm really going to do is say temp equals this, put the number in here, say temp next equals head, so it points at this, and then say head equals temp to no longer point here, but instead point here. Temp still points there, but that's not a problem. So now I'm going to say temp equals malloc again, so now it points at this, put 3 there, temp next equals head. Head, I don't want to point at this anymore, so head equals temp, and it also points here. So what it looks like, drawn better, now is this. Right? So let's keep writing the code to do that. So once again, what I'm doing here is not the way you really want to do it because it's not scalable, but I'm trying to be very explicit. So doing what I just said, I said this is now going to be temp, that'd be temp, that'd be temp, or actually I'm going to change a couple of these values. So this is 2, this is head, and then head equals temp. And now we'll have 3 here, and let's print this out. That's why I created the I variable up here, for I equals 0, I is less than, well actually we're not going to do it this way. I'm going to show you something that's more standard for working with linked list. So I created this P variable, here's why. So I'm going to say P is equal to head, and while P is not equal to null, do something. I'm going to print the current node's value, which is P x, and now P is equal to P next. Let's see what that does. 3, 2, 1. So how does this work? Well, it prints 3, 2, 1 instead of 1, 2, 3 because when I said P is equal to head, P now points at this, the 3, so I'll print it. And then when I write P equals P next, P now is assigned the address here. So now it points to here. I print 2. Then P next takes this address here, assigns it to P, goes to here. Remember here we actually stored null. So after we print 1, we say P is equal to P next, which is null. So then the while loop says while P not equal to null. Keep running. Well, now it is equal to null, so we stop. So in most cases with linked lists, you don't really keep track of how many things you stored. You just put something at the end so you can know when to stop. And that's null, since that's not a valid address. So that's what I just did. So why did I even use P? Why not just use head to move through this? Well, I could have, but what would have happened? Well, head would have kept moving to new things, which means now if I want to reuse this linked list for something, like freeing up the memory, which I haven't done yet, well, where's the head at? If I change the value of head, which finally it would point to here, and actually technically finally it would be null, so it doesn't point to anything, I no longer know where the linked list is at. So I can't free up the memory. So that's actually a common bug that you have to be aware of. If I want to free up the memory, then I can do something similar. So in this case, I don't care about whether or not I reuse head, but I have this code right here. Let's put a printf statement in here. And let's take this code right here and modify it. And now I'm going to say freeing, and we'll print the number that's there. So what do I need to do? Well, if I do this, that does free that memory, but remember that memory contains the address to the next node. So looking at this, let's draw a cleaner picture. So P initially points at this. When I write free P, well now this block of memory is freed up. Where's this block at? I don't know. So before I free this, I need to save the address of the next and then free this. So now I'm going to do this. temp equals P next, and then I'll say P is equal to temp. So now I freed up all that memory. So if I try to do something with it, I'm probably going to have a problem, right? So this is a very explicit way that hopefully shows you the steps, but you really would never do it like this. Or I can't imagine many situations in which this would be the way you do it other than for educational purposes, because it's not scalable. I don't know in advance how many nodes I'm going to need. And even if I did, what if I said, well, I'm going to have 10? Well, I don't have to go through all 10 and explicitly do it, so I want to use a loop for this. So let's talk about that. So what can we do? Well, let's look back at this and see, how do these differ? Well, this, I'm using head instead of temp. So I could have made it look more like this. So I could have done this and said temp. And this would still work. Let's see that. So it does work. The main difference between this and the remaining sections is here I give it a value of next. I give it a value of null, whereas these point to head. So how can I write code that does that for me? Now, one way would be able to say, well, if it's the first node, do it this way, and for every additional node, do it this way. But there's actually a solution to that where I don't have to even do that much work. And that is set head to be null in the first place. So then looking back at my code, if I do this, head's equal to null, well then when I write head right here, I just assign null to this next address. So now this code and this code and this code are all logically equivalent. The only thing that changes is what actual data do I store. But other than that, they're identical, which means I can write a loop to do this work. So that's what I have here. Struct node star head equals null. I create this temp variable, and now temp's equal to malloc, give an initial value, so the loop here also assigns a value. Set this equal to head, head's equal to temp, and now at the end, head will point to the first node in the list. All right? So this would be the streamlined version for this. What if we want to go through the linked list and do stuff with it? Well, remember, we don't typically know how many nodes there are, so I don't want to have a loop that runs a predetermined number of times. So instead, we can do similar to what I did when I was freeing memory or printing the contents, and that is keep going until we reach null. So in this example, I'm looking for a particular number, and once I find it, I say that I found it, and then go through and do this. The answer to this question is what I showed you earlier, which is I could use head to move through it, but then head no longer points at the beginning of the linked list, so I've lost track of it. This is an idiomatic way of doing it, so I could use the while loop. Some people do this. Notice here I've taken the parts and put them into the for loop. So here P is equal to head, while P is not equal to null. Do this and change the value of P this way. So going back to this, initialize, test, change. Initialize, test, change. So that's an alternate way of doing it. So continuing on, we worked with what's called a singly linked list, which only goes in one direction. But there are doubly linked lists, there's circular linked lists, and so forth, probably some others. A doubly linked list has pointers that point to the previous node as well as the following node. All right. So let's look at one last example before we move on and end this video. So I'll probably want functions to do these things, right? I don't put everything in main. So let's see how to do that. So I'm going to have an add node function. So I'm going to say struct node star. This will be the return type. Here's the function name. And what I will give it will be another address to a struct node. So struct node star, we'll call it H here. I could call it head. It's a different head than here. And then int n for a value that it's going to work with. And I'm just going to put all the code here, but certainly I could have a structure, or excuse me, a function declaration here, and then the actual definition below. So what do we need? Well, I still need some of these things. So we'll have struct node star temp equals, we want something like this. That allocates memory. If you don't like doing it all on the fly, then you could do this. It works either way. Then once we have it, I'm going to take these two values. So temp x is equal to the value n that's passed in, and this will be h. And then eventually, I'm going to return temp. So now doing something closer to what we would have done before. Or I is equal to 1, I is less than 5, for example, I plus plus. Head is equal to add node, head, I. The rest of this would be the same. I'm just cleaning up some stuff so we can focus on what we want to see. So let's see what happens. 4, 3, 2, 1. So it's different because I went to 4 this time, but still works basically the same. So how does this work? Well, I pass in the initial value of head here, which is null. So I create my temp node, give it the number that I passed in, and then also assign null here the first time. And then when I write head equals add node, it's equivalent to writing head equals temp, which is what I'd explicitly written before. Then on the next iteration, I pass in the current value of head as well as the next value of I. This creates a new node, ties it to the new head, and so forth. So this code is logically equivalent to what I had before. So I prefer to do it this way in many cases, where I create the temp node and then return the address using this right here. I return the address to be reassigned. But what if for some reason we couldn't do that, or we just chose not to do it? And so instead we want to have the temp variable somehow put its address into the head. So you might think to do this. So we might say this is void, so this won't work correctly, although it probably will compile. We do this, so this won't be returning. So let's see what happens. So it compiles fine, but what happened? Well, I never got any values back. Head never changed. Because how do I get temp into head? So what just happened? So in main, I create a head variable, which means I got a block of memory called head, and it has some address, but I gave an initial value of null. So its address, let's say, is bf00. And then I call the function add node, and I gave it head. And then down here in add node, so I create temp. They gave me the structure. I put in a value that we were passed, right? Like say 3. And then we stored, because we were passing this value, so I did store null here. But I never changed this. I need to change this now. Temp has an address. Temp is pointing at this. So let's say the address of this is AA0C. I need to somehow get AA0C into this spot in memory. So how do I do it? Well, I need a pointer to this pointer. And then I need to dereference this pointer to get to this pointer. That's what needs to happen. So that means this need to be the address of head to pass it, and this will be star H. So H is of type struct node star star. Star H is of type struct node star, which is what head is. So that means every place where I used H before, now I'm going to use this. And did we do anything else? To node. I think that's it. Oh, and then we'll do this. Star H is equal temp. So basically I'm saying head equals temp in an indirect way. Oops. And there it still works. Let's prove it works by changing the message here. So I'm just showing that I am really recompiling it and running it. So it works. So star H is equivalent to head. H just contains the address of head. So I dereference here. All right. So this is another way of doing it. I'll create some more videos showing some more data structures, or in particular we'll do what's called a binary tree. But I also will create more videos showing more examples of working with a linked list.